Hello everyone. I am Yu Huang from the MSTP LMT department. I'll introduce the QoS in this course. Quality of service, QoS, guarantees end-to-end service quality to meet different requirements of various services on packet networks. The bandwidth, latency, jitter, and packet loss rate are four factors that affect QoS. QoS measurement based on these factors provides quality assurance for key services. In today's network communication, people have an increasing demand for higher bandwidth, and different services have different bandwidth requirements. Therefore, bandwidth is one of the major concerns in network QoS design. In this slide, voice transmission is used as an example. The latency refers to the period from the time when one person starts to speak to the time when the other hears it. If the latency is long, voices are unclear or interrupted. A jitter refers to the difference in latencies of different packets in the same service flow. The jitter is caused by different queuing time of the packets and is the major factor that adversely affects QoS. Real-time services such as voice and video services are jitter-sensitive. Voice or video services will be interrupted due to different queuing time of packets. If the number of lost packets is small, services will not be greatly affected. If the number of lost packets is large, services will be greatly affected. Therefore, the packet loss rate is the most concerning QoS factor. The basic idea of the diff-serve model is to classify flows in the DS domain and manage them in a unified manner to achieve the same per-hop behavior, PHB, and guarantee service quality. Per-hop behavior, PHB, is an important concept in the diff-serve model and has several service levels for packet forwarding. CS7, CS6, and EF guarantee service forwarding quality. AF4, AF3, AF2, and AF1 queues allocate bandwidth based on the weights of the queues. The BEQ does not guarantee service forwarding quality. The table in this slide describes the default mapping between priorities of ingress packets and PHB service levels on an OSN device. The table in this slide describes the default mapping between priorities of egress packets and PHB service levels on an OSN device. Traffic classification is classified into simple and complex traffic classification. By using simple traffic classification, a device can map a VLAN priority, IP-DSCP value, or MPLS EXP value to a PHB service level, or map a PHB service level to a VLAN priority, IP-DSCP value, or MPLS EXP value. Complex traffic classification classifies service traffic according to multiple fields in packets, including the source IP address, destination IP address, source port number, destination port number, and VLAN ID. Then these fields are mapped to PHB service levels. CAR is a traffic policing technology. OSN devices support CAR policing for traffic that undergoes complex traffic classification in the ingress direction. If the rate of a packet is lower than the CIR, the packet is marked green and preferentially forwarded. If the rate of a packet is higher than the CIR, the packet is marked red and is discarded directly. If the rate of a packet is between the CIR and the PIR, the packet is marked yellow. You can configure the traffic behavior for this packet, such as discarding, passing, or remarking. Remarking indicates that traffic marks are mapped to other PHB service levels. When the rate of passing packets is lower than or equal to the CIR during a time period, forwarding of certain burst packets is allowed, and these packets are preferentially forwarded in case of network congestion. The maximum size of burst packets is determined by the committed burst size, CBS. When the rate of passing packets is higher than the CIR but lower than or equal to the PIR during a time period, burst forwarding of certain packets is allowed, and these packets are marked yellow. The maximum size of burst packets is determined by the peak burst size, PBS. Traffic shaping limits the traffic and burst of an outgoing connection on a network, and therefore ensures that packets are evenly transmitted out of the network. when the buffering queue has no packet. If the traffic rate is lower than or equal to the PIR, the received packets are directly forwarded. If the rate of packets exceeds the PIR, the packets are put into the buffering queue. If the rate of packets is constantly lower than or equal to the PIR, but it suddenly exceeds the PIR at a later time, the burst forwarding of some packets is allowed. The maximum size of burst packets is determined by the PBS. When the buffering queue has packets, if the buffering queue is not full, the packets that exceed the PIR are put into the buffering queue, which then forwards the packets at the specified PIR. If the buffering queue is full, the newly arrived packets are dropped directly. When network congestion occurs, the device provides different service levels by using queue scheduling policies. SP scheduling is performed strictly according to the priorities of queues. Only when the queue of a higher priority is empty, the queue of a lower priority can be scheduled. If high priority packets are congested, low priority packets cannot be scheduled. The WFQ algorithm allocates a weight to each queue and then allocates bandwidth to each queue according to its weight. In this slide, a bandwidth of 100 megabits per second is used as an example. If the weights for the 4 queues are in a proportion of 5 to 2 to 2 to 1, the bandwidths for the 4 queues are 50 megabits per second, 20 megabits per second, 20 megabits per second, and 10 megabits per second, respectively, when each queue is congested. If the first queue is empty and the other 3 queues are congested, the bandwidths for these 3 queues are 40 megabits per second, 40 megabits per second, and 20 megabits per second. Low priority packets can eventually be transmitted at last by using the WFQ scheduling algorithm. The SP plus WFQ scheduling mode is used for OSN devices. SP scheduling is used for queues of high priorities, such as CS7, CS6, and EF. Packets in these queues are preferentially scheduled. WFQ scheduling is used for AF4, AF3, AF2, and AF1, which are scheduled by weight. The priority of BE is the lowest. When network congestion occurs or is exacerbated, the congestion management function discards certain packets based on specified criteria to ensure quality of high-priority services. Drop policies include tail drop, random early detection, RED, and weighted random early detection, WRED. Tail drop indicates that newly arrived packets are discarded when a queue is congested. RED indicates that packets are randomly discarded when the length of a queue reaches the threshold. Upper and lower thresholds are set for the queues by using the WRED policy. If the queue length is lower than the lower threshold, no packet is discarded and the packet discarding probability is 0%. If the queue length exceeds the upper threshold, all newly arrived packets are discarded by using the tail drop policy, and the packet discarding probability is 100%. If the queue length is between the upper and lower thresholds, packets are discarded according to their colors. Green packets have the lowest drop probability and maximum lower and upper thresholds. Yellow packets have a medium drop probability and medium lower and upper thresholds. Red packets have the highest drop probability and minimum lower and upper thresholds. OSN devices support HQOS based on the port VUNI ingress, VUNI egress, PW, and QNQ. The table in this slide lists the QoS scheduling policies supported by each level. That's all for this course. Thank you.